Hello guys, my name is IBM and today I would like to record paper 5, that is planning, analysis and evaluation. Do not forget to visit our website www.caieresourcemaster.com where you'll find free past paper questions. You'll find their topical questions for AS and A level. So just visit the website. When you visit the website many times, you make it eligible to have ads so that it can be monetized with ads. Okay, so I will take much time on this paper. I may not take exactly 1 hour and 15 minutes because I want to give a lot of explanation. And this will be helpful and you will use the same understanding for other different papers. So let me go to the questions directly. So question number one, the way I present this work is how I encourage my students to do their work. It may not be final. You might have been taught differently, but the final output is supposed to be the same. The aim is to score as more marks as possible in paper 5. So question number one is always planning an experiment, and this is the question where many students get 0 out of 15. However, if you master the ideas behind how you should plan your essay, you can't really get 0. You can't even get less than 8 on this question paper. So normally I encourage my students to first come up with a skeleton of what they will be writing in their essay. I always encourage them to use this space here, this page, for outlining what they are going to be dealing with. So as you're reading through the question, you are thinking about the measurements you're going to take and the instrument you're going to use. So we start. A thin cylindrical bar of length L. First of all, the bar is cylindrical, the length is L. To measure L, most likely I will use a ruler. So you have that in mind, you'll use a ruler. And cross-sectional area A. So to determine cross-sectional area A, I will need to measure D, which is the diameter. And because it is cylindrical, and it is a fin, the diameter could be measured using a micrometer screw gauge. And of course, when you measure the diameter, you have to repeat measurements along the magnet or along the length of the magnet and obtain the average. So you'll find the average diameter, and then you'll find the area from area equals to pi d squared over 4 is attached to. So here, if I have this, I have micrometer screw gauge taking average diameter. It's like I have so many marks already. If I add this in my essay, an identical magnet is attached to a trolley as shown in the figure. Okay, so this is the figure. So I have talked about how to measure L. The trolley is held so that the separation of the north pole of the two magnets is S. So I'll measure S. I may measure S using either the inner jaws or the inside jaws of a vernier caliper, or I could measure S also using a ruler, but I'll just say because to produce a good force, S will be very small, so I'll measure this using a vernier caliper. Okay, point P is a distance D from the north pole of the magnet on the stationary trolley. So I'll put, to easily measure D, I'll put a reference mark on this end. I may put a reference mark here, I may put a card on this end, and then I measure D, and I'll measure D using a ruler. The trolley is released, and I may put a block here to hold the trolley before releasing it because I need to prepare myself to release this. So I may put a block here. This could be a block. But remember, when I bring um, north to north, this may push the other block. So to secure this, I may use a G clamp. So I will secure this block using a G clamp. So this is a G clamp. Okay. So I'll secure that using a G-clamp. All those things I'm adding here, they are just creating more marks for you. So here, before I even write an essay, all the points I've talked about will give me about 80 marks before I even write the essay here. So the speed V of the trolley at point P is determined using one light gauge. So we are going to put a light gauge here. So I'll put a light gauge here. Let's say this is the light gauge. Whatever you draw, you just label it. So this is the light gauge. So I'll try to clamp it. So let me put a clamp here or a stand. Remember, this is just the skeleton. So I'll have a clamp, a stand with a clamp to hold the light gate. Of course, the light gate must be connected to a timer. So I'll put a timer somewhere. So this is the timer. Okay. But then I may want it to stop. I may want the trolley to stop when it passes point P. So again, I'll put a block here, a block to stop the trolley. Okay. So it is suggested that V is related to S by that relationship. Now we have already seen V is the speed. The speed is going to be dependent on S, where S is going to determine the force of repulsion between the two poles. So it means S is going to be the independent variable, which I'm going to be changing as the experimenter, and therefore V is going to be the dependent variable, which is going to change when I change S. And how will I determine V? To determine V, I may use a simpler method. Maybe I will attach a card onto this trolley, whose length I will call X. I will measure X using a ruler. So X is going to be measured using a ruler. I've attached a card onto the trolley. I measure the length of the card and I will look for the time for which the card interrupts the beam. So I will look for T using a stopwatch. T using a stopwatch. I've measured X using a ruler. Then I will determine V by dividing X by T. So that will be the average speed at that point P. Okay. Of course, I will have to repeat. I repeat V for the same S and obtain the average. So repeat. I'll repeat and get the average of V. Okay. Now I'm going to analysis. Now I have how the experiment is going to flow. Now I'm going to analysis. Analysis, you look at this equation here. Because S is the independent variable and V is the dependent variable, I'm going to try and make sure anything related which has V alone is the subject. So I will make V squared the subject. So that equation, making V squared the subject, so I have that V squared is going to be equal to twice 2D K A squared B squared L squared. Divide this by M. Then there is 1 over S. Because S is the independent variable, I'll also separate S at S so that I'll have 1 over S power 4. Then it's minus Q times 2D, because I'm making V squared the subject, so it is 2D cubed minus 2DQ, also divide by M. So I have made V squared the subject. So normally we prefer to put the dependent on the y-axis and the independent on the x-axis. So it means I'll plot a graph of V squared against 1 over S power 4. If I plot V squared against 1 over S power 4, it is going to be a straight line. A straight line is going to show that the relationship is valid. The straight line goes through, it is going to go through a negative 2dq over m. That is the y-intercept. The gradient, of course, the gradient of this line is going to be equal to 2d k a squared b squared L squared divided by m. So that will be the gradient of this graph. So it means they said plan a laboratory experiment to test the relationship. So the relationship is going to be valid if it is a straight line that goes through this negative 2dq over m, whose gradient is this. Then draw a diagram. I'm going to draw a beta diagram. Explain how the results could be used to determine k and q. So here I just make, because the gradient is equal to that, so it means my k is going to be m times the gradient, and this is going to be divided by 2d a squared b squared times L squared, that is k. And then q will be found from the y-intercept. So q is going, because the y-intercept is negative 2dq over m, so q is going to be m times the negative y-intercept, then divide by 2d. Okay. Then for safety, I think I've already talked about safety. I've placed a block here to stop the trolley when it passes point P. So for safety, I've already added a block. You could put a cushion beyond P to stop the trolley. When I add this to a diagram, I may not even write it in an essay. The examiner will know that that is a safety precaution. Okay, now I will go to the page where I have to present my work. I have now this is called the skeleton of the plan. Now it becomes very easy for me to draw or to write the plan. So to start with, I'll draw the diagram. Normally the diagram is a modification of what has already been given in the question. So I'm just going to draw this skeleton in a better diagram. Make sure your diagram looks nice. Sometimes the examiner may also mark by impression, if the work is so much disorganized, and the examiner is also a human being. He gets annoyed, he gets tired. So if your work is not pleasing, the examiner may be biased. So you can draw a better diagram using a ruler. So this is going to be the bench or the table. So let's say this is the bench. So I'm going to mark point P somewhere here. Point P somewhere there. I'm going to put a light gate somewhere here. Like I said, you can draw a better diagram using a ruler. So I'm going to put a block. This is going to be a block. I'm going to put a block here to stop the trolley. Let me first draw the stand so that I minimize the space. So this is the stand. I'm just going to put a block on this stand. So this is the block to stop the trolley. On this block, I will just, because I don't have enough space, I'm going to put the timer on this block. So this is going to act as my timer, digital timer. Then I'm trying to clamp this. So this is a stand. Sorry, that is the clamp, not the stand. And this is the light gate. Okay, so I think I'm done with that side. Now this side I have to draw the trolley. So I have to, like I said, I will clamp this. So I'm going to put a G clamp. Let me change the color here for the G clamp. So the G clamp is to secure this block. So now I'm going to draw the trolley. So on this trolley, I'm going to attach a card. Let me use a different color for the card, because I want to use this card to the length of this card to measure the speed at point P. So this is going to be a card, and I will say its length is X. Okay, so you may want to measure the separation here. And this was called S. Then the distance, this one was called D. Then the length, which length am I remaining with? The length of the magnet, this was called L. Of course, I may be forced to put a card here to help me in measuring D or in measuring S. So you may put a reference card here to help you measure. So this could also be a card to help you measure distance D. A card attached at the extreme end here. So these are the magnets. I have to label them. This is the trolley. Magnets. Then let me just ignore the block that I would place here to hold the trolley, because I can hold the trolley in my hands after measuring a distance S. Then I release the trolley so that it now moves. So I think I've drawn almost everything that I need for this experiment to be successful. Try to label as much as possible so that you can get that 1 mark for clear labeling, because you may not have used the conventional symbols. After all, some apparatus do not have conventional symbols. Okay, now I can write my essay. If you have a diagram like that, this diagram has a lot of marks, because some of the things that I've added here could be awarded or could have been awarded in additional details. But by adding them here in the diagram, then they may not be awarded in additional details, but they could be awarded here. For example, I have the block to stop the trolley. I've attached a card. I have clamped this. Yes, I've clamped this. So it's like I have three marks. I've also added a card here to help me measure D. That could also be an improvement. I have my light gate has been connected to a timer, so the diagram has almost 4 marks from additional details. Okay, so let me write the essay now. So the way I write my essay may not be the same way your students write it, may not be the same way you teach your students to write the essay. It may not be fine, or you can write your essay the way you want, the way you see it flow, but what is very important is that your essay should flow. Ensure that the experiment is workable in the laboratory. So I would say in this experiment, In this experiment, S is the independent variable, and V is the dependent variable. So that is one. You have to talk about which variables should be kept constant, and don't just call them control variables. You should tell the examiner that these ones should be kept constant. So the distance D through which the trolley is going to be moving is going to be kept constant. That means every time I change S, I must shift P so that the distance D remains constant. So D should be kept constant. What else is going to be kept constant? From the equation, I think I didn't mention the quantities to be kept constant. D should be constant. The length of the magnet should not change. The cross-sectional area should not change. The mass should also not change. And I think the magnetic flux density should also not change. So all those ones should remain constant. So I'll also add that L, A, the mass, and B, that is the magnetic flux density, should also remain constant. Then to collect and analyze data, I'm going to take the following steps. So one, I'm going to measure. So let me set to collect and analyze data. I'm just saying I will because it is me going to carry out the experiment. You can write your essay the way you want. I will take the following steps. So number one, I'm going to measure the mass, of course, using a top band balance. I'll measure the length L using a ruler. I'll measure D using a ruler. I'm going to measure B using a hollow probe. So measure M using a top band balance. D L and D using a ruler. Number two, I'm still taking measurements. I've not yet measured or determined the magnetic flux density. So let me first measure the magnetic flux density. Maybe let me first measure the diameter. So measure the diameter D of the magnet, small d of the magnet, using a micrometer screw gauge. using a micrometer screw gauge. Of course, this one is done at different points along the magnet. At different points along the magnet. At different points along the magnet, measure the diameter D at different points using a micrometer screw gauge along the magnet and obtain an average diameter. So here I have two marks in one point. You're measuring diameter using a micrometer screw gauge, but then you are trying to improve the measurement of diameter by taking different measurements along the along the magnet and obtaining the average. So now we can calculate or determine the area. So 3, determine A from area equals to pi d squared divided by 4. Because we have the diameter, then the area is pi d squared divided by 4. Then point number 4. I'm now also going to measure the magnetic flux density B. So measure B. Of course, we measure B using a Hall probe. Of course, whenever you are using a Hall probe, your teacher must have told you that you first use it in one direction, then you use it in the opposite direction and obtain the average value of B. So measure B using a Hall probe. First in one direction, then in the opposite direction, then in the opposite direction, and obtain the average value of B. And obtain the average value of B. Of course, you would also measure using a calibrated Hall probe, where you just adjust the probe until a maximum value is obtained. I'll just write that in a different color because it's just an alternative. Let me use green. Or you would say measure B using a calibrated Hall probe and adjust the probe until a maximum value of B is obtained. So if it's not calibrated, we just look for the average value of B, as have demonstrated in that first alternative. Okay, so that was step 4. I still have around 10 minutes for one because each question should be around 45 minutes. So point 5, I've finished to measure B, I've measured A, I've measured M, I've measured L, I've measured D. I'm only now going to measure S. But before moving to that, I have to ensure that B is high enough. So I have to use a very strong magnet so that V is large enough. So where should I write it? Measure B using a hollow probe first in one direction, then the opposite direction, and obtain the average value of B. So I'll just write a point here and say use a very strong magnet. Ensure that the magnet used is very strong. So that V is large enough. Of course, if V is large enough, then the percentage uncertainty would be low. Then 6, I'm now going to measure S. So measure S. Measure S. Of course, S could be very small. So measure S using a vernier caliper. You can use the inside jaws using a vernier caliper. Using a vernier caliper. To make S easier to measure, you place a marker to the left of the trolley to increase accuracy in measuring S. Place a marker to the left of the trolley. To increase accuracy. To increase accuracy in measuring S, of course, and D. Then step number 7, I think I have not measured the length of the trolley which has been attached to the card. Measure the length of the trolley. Measure the length of the card. Measure the length of the card. Let me first edit this. Let me say measure the length X. Measure the length X of the card attached the trolley. Attach the trolley. Of course, this is using a ruler. Now I'm going to release the trolley after I think I've measured almost everything. So step 8, release the trolley. Release the trolley. And record the time. I'll call it T. The time T for which the card interrupts the beam of the light gate. So release the trolley and record the time t for which the card interrupts the beam of the light gate. Okay, now I have t and I have x. I'm going to determine the speed v. So step 9, determine the speed. Determine the speed v at p from v equals to x divided by t. Now we are going to repeat the experiment so that we get an average of v for the same s. So repeat experiment for the same s. For the same value of s, and obtain an average value of v. Okay, at this point I've written a lot of marks, but I've not yet reached analysis. So 11, I'm now going to repeat the whole experiment for different values of s and obtain at least 6 sets of values. So repeat the experiment. Now for different values of s, because s is the independent variable. Until you have 6 sets of values. So we need 6 sets of values because we want to plot a graph. Then question 12. Now this part is where students always forget. They skip this part, yet is making the subject trying to rearrange the equation gives you a mark. So I'll say from mv squared over 2d equals to, I think it was k a squared b squared l squared over s power 4 minus q. It implies that when I make v squared the subject, it is going to be v squared equals to twice d, I think k a squared b squared l squared over m times times 1 over s to the power of 4, then minus that becomes 2dq divided by m. So now I will tell the examiner that I will plot a graph. So 13, I will plot a graph of, so from that equation, if v squared is on the y-axis, then 1 over s to the power of 4 is going to be on the x-axis. So I will plot a graph of v squared against 1 over s to the power of 4. Of course, that is a straight line. So I'll just simply say that a straight line, here I can just outline and say a straight line now this line is not through the origin, so a straight line passing through negative 2dq over m shows that the relationship is valid. Shows that the relationship is valid. It shows that the relationship is valid. Okay. And then, of course, from that equation again, we can see that k, of course, the gradient equals to 2dka squared b squared l squared over m. So it means k is m times the gradient. So k equals to m times the gradient divided by a squared l squared b squared times 2d. The order doesn't matter. And then q, because the y-intercept is minus, of course you are comparing with y equals to mx plus c. The y-intercept is minus 2dq over m. So making q the subject, so q is going to be equal to the negative of the y-intercept times m, divide this by twice d. Okay, I think that is analysis. Then maybe for safety, a block or cushion placed beyond P stops the trolley. Okay, so that is my essay. I've used excess of 3 minutes on that question. Let's move to question number 2. A student investigates an electrical circuit, a power supply of EMF ES. So ES is EMF power supply. A negligible internal resistance is connected in series with 3 resistors, each of resistance Z. A cell, an ammeter, and a resistor of resistance R are connected in parallel across one of these resistors as shown. The current I is measured by the ammeter for different values of R. It is suggested that I and R are related by the equation 3E minus ES equals to I into 3R plus 2Z, where E is the EMF of the cell. A graph is plotted of 1 over I on the y-axis against R on the x-axis. So what does this statement tell us? I'm going to try and make 1 over I the subject, because 1 over I is plotted on the vertical axis. So I should try and make it the subject. So this is going to give us, this is the same as 3E minus ES divided by I equals to 3R plus 2Z. Because the graph plotted is of 1 over I, so I'm making 1 over I the subject. Therefore, I will say 1 over I is going to be equal to 3 divided by 3E minus ES. Of course, this is times R plus 2Z. I'm dividing everything by 3E minus ES. When I compare this with the equation y equals to mx plus c. You notice that on the y-axis I've plotted, they have put x. So on the y-axis is 1 over I, on the x-axis is r. So the gradient is 3 over 3e minus es, and the y-intercept is that. So the gradient is going to be 3 divided by 3e minus es, and then the y-intercept is going to be twice z divided by 3e minus es. Okay, so this is the y-intercept. Values of r and I are given in the table. So these are values of r, and they've given us the values of I. Okay, so calculate and record values of 1 of I in the table. Include the absolute uncertainties. So here are the rules of significant figures. Because I values are to 3 significant figures, there are 3 significant figures, all of them, because even though this is varying, these are 3 significant figures. So I'll write, so it means these zeros are as a result of rounding off, because the other digits are not zero. So these will all be to 3 significant figures. So I'll just substitute the values. Now note that the units here are microamperes and this is per ampere, so I have to be very careful with that. So I'll say 1 divided by, open brackets, 194 exponent minus 6. So that is 5154. So you can write 5155 or 5150 to 3 significant figures. So I can write 5155, 5155. The rule allows to increase the number of significant figures, but for me I will consider 5150 plus or minus. Okay, the second one, 1 divided by 180 exponent minus 6. So that would be 5556. 5556, but I'll just write 5560 plus or minus. The next one is going to be 1 divided by 172 exponent minus 6. 5814. 5814. I'll just write 3 significant figures. 5810 plus or minus. The next one is 1 divided by 160 exponent minus 6. So that is 6250. 6250 plus or minus. 6250 plus or minus. The other one is 1 divided by 150 exponent minus 6. So it is 6667. 6667. I'll just write 3 significant figures. 6670 plus or minus. Then the other one is 1 divided by 144 exponent minus 6. So that is 6944. 6944 to 4 significant figures. I will just write 6940 to 3 significant figures. So the rule allows you to maintain the number of significant figures or to increase. If you're not sure, it's rather you rather write more significant figures so that you don't lose the mark for this column. Then for the uncertainties, so we have that, let's say that y equals to 1 over I. So it means the uncertainty in y is going to be equal to the uncertainty in I divided by I, because this is a fraction. So this one is of course the same as I power 0 divided by I power 1. So we treat it the same way we treat division and multiplication. So absolute uncertainty in y is going to be a fraction in I over I times y, which y is 1 over I. For example, for the first one, the absolute uncertainty in 1 over I for the first one is going to be the absolute in I is 2 divided by I, which is 194 times 1 over I, which is 5515, 5150, which is, so we have 2 times 5150 divided by 194. So that is 53, which is approximately 50. So this will be plus or minus 50. So I'll just use the same formula for the rest. Absolute is 2 times 5560 divided by 180. I'm not using power minus 6 because the absolute and the true value have the same unit, so they cancel out. So this is approximately 60 to one significant figure. Absolute uncertainties are good enough to one significant figure. It even makes plotting easy. Then 2 times 5810 divided by 172. That is approximately 70, rounding off to one significant figure. Then we have 2 times 6250 divided by 160. That is 78, which is approximately 80. Then we have 2 times 6670 divided by 150. That is 88.9, which is approximately 90 to one significant figure. Then we have 2 times 6940 divided by 144. That is 96, which is approximately 100. Okay, so now what remains is plotting. Include absolute uncertainties in 1 over I. Plot a graph of 1 over I against R in kilo ohms. Include error bars for 1 over I. Because 1 over I is on the vertical, it means the error bars are going to be vertical. Draw the line of best fit and the worst acceptable straight line on your graph. Label both lines. Do not always forget to label. This is where students lose the mark. Determine the gradient of the line of best fit. Include the absolute uncertainty in your answer. So we are going to find the gradient of the best fit. We shall also find the gradient of the worst fit. And then for the uncertainty, we shall subtract. Okay, let's first plot the points. So plotting, I'll write the points on my paper here. 5150, 556, 581, 6250, 6670, 6940, 1.5, 1.75, 1.92, 2.22, 2.48, 2.72. Okay, now let me plot. So the first point we are plotting is 5150 against 1.5. So this is 1.4, 1.6, 1.5 is in the center. The only problem is looking for 5150. So 5, the scale on the vertical is 200 divided by 10. It means each of these boxes is 20. I hope so. 5200 minus 500 divide by 10. Each box is 20, so the scale on the vertical is 20, and the scale on the horizontal is, I think it is, let me see, the scale on the horizontal, 1.6 minus 1.4 divide by 10, 0.02. On the horizontal, each small box is 0.02. So I now want to plot 5150 minus 500. Divide this by the scale, which scale is 20. So I'm going to add 7.5 boxes on 5,000. So I have 5, 6, 7.5. So this is the point. I'm going to try and magnify this so that it is easier for us to see. It is in the middle of the box. Now those points which are normally in the middle of the box, the examiner pays much attention on them, so you must be very careful while plotting them. Then the next point is 1.75. This is 1.7. Remember, each box is 0.02, so 1.727475 is in the middle of that box. It is plotted against 5560. So 5560 minus, what is the nearest? The nearest is 5400 minus 5400. Divide by the scale on the vertical, which is 20. So I'm going to add 80 boxes on 5400. So these are 5, 6, 7, 8. So the point is going to be here. Okay. Then the next one is 1.92. This is 1.92, because each box is 0.02, so 1.92 is here. 1.92 is plotted against 5810. 5810. I think this, because each box is 20, so 5810 must be in the middle of this box. I think that is the point. Then the next one is 2.22. 2.22 is one box added. 2.22 against 2.22 is against 6250. So this is 6250. I think the nearest is 6200. So I'll say 6250 minus 6200 divide by 20. Those are 2.5. So I'm going to add 2.5 boxes. So 1, 2.5. So the point is here in the middle of that box. Then the other point is 2.48. 2.48. So this is 2.5, 2.42444648. 2.48 is against 6670. 6670 is just above 600. So I'll check my calculator. 6670 minus 6600 divide by 20 on the vertical. So 3.5 boxes. So I'll add 3.5 boxes on 600. So 1, 2, 3.5. So the point is going to be here. Okay. Then the next one is, the last one is 2.72. So 2.7 is here, 72 add one box. Okay. 2.72 is against 2.72 is against 6940. 6940 is just above. So let me check with my calculator. 6940 minus 6800. So it's 140 divided by 20, 7 boxes. So on 6800, I'm going to add 7 boxes. So 1, 2, 3, 4, 5, 6, 7. Okay, so plotting is done. I can now draw the line of best fit. But before doing that, I can also draw the error bars at once. Because drawing the error bars is very easy. Please use a ruler to draw the error bars. Do not put extra marks on your graph like I've been doing. You just put there a ruler to see the correct point. Draw a small circle, don't make the circle exaggerated. So let's draw the error bars. The first one was 50. Remember the scale on the vertical is 20. So if we are plotting 50, so 50 divided by 20, that is 2.5 upwards, 2.5 downwards. Remember this point is in the center of the box, so it is 0.5. So I'll just add 2 above, 1, 2, so this will be the point. Then a half, 1, 2, this is the point. Use a ruler and draw a very neat error bar. When you pass there the pencil several times, it becomes very beautiful and visible. The second one is 60. 60 is, I think 60, those are 3 boxes upwards and 3 boxes below. Please use a ruler to draw very neat error bars. So 1, 2, 3. Then 1, 2, 3. I try to make the length of these to be 2 small boxes, 2 small squares. But now this point is in the middle of the square. Please use a ruler to draw a very neat error bar. Then the next one is, like I said, you can pass there the pencil several times so that it looks very bold and visible. The next one was, I think, 70. I think 70 is 3.5 above and 3.5 below, but this point is in the center of the box. So I'll just say a half, 1, 2, 3. So this will be here. Then a half upwards, then 1, 2, 3. I think that is 70. Use a ruler to draw a very neat error bar. The next one was, I think, 80. 80, I think it is 4 upwards and 4 downwards, but this point was in the middle of the box. So how do I count 4? This is a half, 1.5, 2.5, 3.5. So I must add half, so this will be in the middle of the box. So half upwards, 1, 2, 3. Then I add the middle of the box. The examiner pays much attention on these points which are in the middle of the box. So use a ruler to draw a very neat error bar. And the next one was 90. I think 90 is 90 divided by 20. 90 divided by 20 is 4.5. So I'm going to count 4.5 above, 4.5 below, but this point was in the middle of the box, so I'll just count 4 1, 2, 3, 4. So that is 4.5. Then a half, 1, 2, 3, 4. Then the other point, the last point was, I think, 100. 100 divided by 20 on the vertical, I think those are 5. So count 1, 2, 3, 4. 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5. Okay, so we now draw the error bar. Please use a ruler to draw very neat error bars. Okay, so those are the error bars. So I'm now going to draw the line of best fit and the line of worst fit. Unfortunately, to draw the line of best fit and line of worst fit, I must fit this graph on the same page so that judgment becomes easier for me. Otherwise, if I don't do that, then it will be hard for me to do that. So I have to make this look smaller and smaller to fit on the same page, because you must use a ruler when everything is on the same page. Now, I have to balance the points to draw the line of best fit. My line may not be the best, but this is just for learning purposes, for instruction purposes. So you judge the points so that they are well balanced above and below the line. Okay. You can draw a better line of best fit. Me, I've drawn that one, leaving 1 point above and 1 point below. So you can draw a better line of best fit. Do not just join the first and last point. No, you try to judge the points very carefully. So that is the line I've drawn. I try to aim at leaving 1 point above and 1 point below. It may not be the best, but the aim is to make sure that the points are well balanced above and below the line. Just like I'm saying, make sure you judge the points correctly. And if you are drawing this on a question paper, your line is going to leave 1 point above and 1 point below. It will leave this point here. It will leave this point at the bottom. If you are very careful, I will not repeat the line of best fit because I don't have the time. Okay, so this is going to be the line of best fit. Let me first do the line of worst fit before I label the lines. So for the line of worst fit, I will draw the steepest. Of course, still you must ensure that the grid fits on the graph paper. Maybe let me change the color for the line of worst fit. Let me use yellow. Maybe it will be visible. Just for learning purposes, I'm using a different color. In the exam, you can draw the line of worst fit with a pen if you are very sure that you have made the right judgment. So I can join the top of the top error bar to the bottom of the bottom error bar, but only if all the error bars are being crossed. When I look at my judgment, I see that they are all being crossed. So I'll draw that one. The top of the top error bar to the bottom of the bottom error bar. And it appears as if all the error bars are being crossed. When we say being crossed, the least it should touch is this point here. and I see as if it is actually touching this point here. So it means all the error bars are being crossed. I don't know whether yellow is visible, but let me change the color for that. Let me use, maybe I should use, should I use brown? I'm trying to join the top of the top error bar to the bottom of the bottom error bar, but ensuring that all the error bars are being crossed. If they're not being crossed, of course, you add just to ensure that they're all being crossed. So you can draw a better line. You can draw a better line than mine. All I'm doing is to give you a picture of what is expected of you. Then labeling, we are going to label, let's call this one the line of worst fit. So that will be worst fit, and this one is going to be the best fit. So I can adjust this. So best fit, worst fit, that is enough labeling. The arrows are pointing to the line. Then the next thing is, of course, to draw the triangles. You may choose the same one triangle for both, or you can draw more than two. You can draw two triangles. I prefer to draw one triangle for both. I'm going to use the color green for the triangle, just for learning purposes and clear elaboration. So you choose points where the grid lines intersect. For example, at the bottom, I'm looking for 2 points. Because my lines are not perfectly straight, since they are drawn on a computer, I may not choose perfect points through which the grid lines intersect, but I'll try my level best. So I'm looking for points where the grid lines intersect. For example, most probably these would have been two good points, this one and this one here. They're not perfectly intersecting, but it's because my line is not perfectly horizontal, not perfectly straight at this point. But this would have been a very good point for me. So put there your ruler and draw a right angled triangle to be used for finding the gradient. Then at the top, let me look for points. I'm looking for 2 points where the grid lines intersect. For example, this one and this one here. So put a ruler and draw a right angled triangle. Now you notice that I've not used the end of the plotted points. It is childish to use plotted points for the triangle. Okay, so that is my triangle that I'm going to use to find a gradient. So I will just, first of all, I'm going to write out the values on paper so that I don't come back here, just go to the gradient. So for the best fit, let me just write the values, readings on paper. So I'm reading the value here and the value here. So best fit, the best fit is the one in blue. The X value is approximately 1.5, 0.52, 54, 56, 58, 1.58, and the Y value is 5,000, I think it's 5,500, 5,300. Then for the worst fit, the one in yellow and brown, That's 1.62 against 5,300. So here we have, this side we have 1.62, 5,300. Then here I have 1.58 and 5,300 for the best fit. Then for the worst fit, I mean for the second pair of points, let me change this to blue for visibility. So for the best fit, I have this point here on the x-axis, that is 2.7. 2.7, I think it's 2.7 for both. Then on the y-axis, so on the x-axis they have both 2.70. This one also has 2.70. Then on the y-axis, best fit has, let me see, 1, 2, 3, 4, 5, 6. 6 times 20, that is 6 times 20, that is 120 plus. I'm adding 120 to 6, 800. So that is 6, 920. So I think this is 6, 920. Normally we're not allowed to write in this margin. Then this one on the y-axis, I mean on the vertical, it is I think 700. I mean 7,000. Okay, so those are the points which I'm going to use for the gradient. For the best fit, the second one is 6, 920, and the other one is 7,000. Okay, so let's go and calculate the gradient of best fit. So the gradient for the best fit is going to simply be using the best fit values. So we have 6, 920 minus 5,300 divided by 2.70 minus 1.58. For the worst fit, we had values such as 7,000 minus 5,300 divided by 2.70 minus 1.662. Okay, I don't think there are powers of 10 here. There are no powers of 10. This is of course kilo. My answer will be in kilo. So when I press my calculator for the first one, we have 6, 920 minus 5,300 divided by 2.7 minus 1.58. So that is 1446. Then the second one is 7,5300 divided by 2.7 minus 1.62. So this is 1574. Of course, the gradient of the second line must be bigger because the worst fit was steeper. Then for the uncertainty, we just subtract 1574 minus 1446. Remember, zero uncertainty is not acceptable. So that is 128. So the gradient is going to be 1446 plus or minus 128. Okay, then last page. Determine the uncertainty of the line of best fit. Determine the y-intercept of the line of best fit. Include the absolute uncertainty. So we just use the equation for best fit. Because they want the uncertainty, it means I'll get the uncertainty for the best fit, the uncertainty for the worst fit, and subtract them. We know that y is equal to mx plus c. So I'll say c for the best fit is going to be equal to the y value. I'll use the same values that I used for the gradient. So the same values, I'll use the first pair of values. For best fit, I'll just use the first pair of values that I used for the gradient. The y value was 5300 minus c is equal to y minus mx minus the gradient was 1446 times the x value, which is 1.58. So we have 1446 times 1.58. So we have 5,300 minus the answer. So it's 3015. Then I will get C for the worst fit. I will use a pair of values that I used for the worst fit, finding the gradient of the worst fit. The y value was also 5,300 minus the gradient of the worst fit was 1574. 1574 times the x value, which is 1.62. So we have 1574 times 1.62. So I'll say 5300 minus the answer. So this is 22750. So the uncertainty is going to be the difference. The uncertainty is going to be 3015 minus 2750. 3015 minus 2750, that is 265. So the uncertainty here, the y-intercept is going to be 3015 plus or minus 265. I hope I wrote plus or minus on the gradient. Yes. Okay, then the next part, use your answer. Your answers to A, C Roman 3 and C Roman 4 determine the values of E and Z, include appropriate units. Okay, so remember earlier on we saw that the gradient was equal to 3 over, I think it was 3E minus ES. When we try to make E the subject, E is going to be, you cross multiply, divide, so this becomes 3E times the gradient, so the other one becomes plus, so this becomes a 3 plus ES. Then I divide this by the gradient, goes to 3E, so it will be divided by 3 times the gradient. This one also divide by 3. Okay, I'm trying to make E the subject, of course. So that is, so it means E is going to be the same as 1 divided by the gradient plus ES divided by 3 when you make E the subject from that equation. Then I'm going to make a substitution here. So this is 1 over the gradient of base fit was 1446 plus, remember this, okay, plus E, which is 2.20 divided by 3. Now remember the gradient, we didn't change the units. The gradient on the vertical, it was ampere. On the y-axis, it was kilo ohm. But now ES is in volts. And in order for us to add, I must change the units for the gradient so that they can't be per ampere. They should be per ampere per ohm. So I have to remove the kilo. Initially, they are per ampere per kilo per ohm. So the gradient was 1446 per ampere per kilo ohm. So if I change this to be 1446 times 10 to the power of minus 3 per ampere per ohm. So I'll just multiply this by 10 to the power of minus 3. Okay, before I add. So this is just rough work for us to know how to change these units. So I'll just convert this. So this is going to be 1 divided by 1446 exponent minus 3 then plus 2.20 divided by 3. So that is 1.4. That's 1.42 to three significant figures, 1.42. So E is going to be 1.42 because I changed the resistance. I changed the gradient to have SI units, and E is EMF. I'll just put here volts. Then for Z, you also remember we said Z, we had an expression for Z with the y-intercept. Twice Z over 3E minus ES is the y-intercept. So twice Z over 3E minus ES was equal to the y-intercept, which means a Z is going to be equal to a half into 3E minus ES times the y-intercept. So I'll make a substitution. So this is a half into 3 times 1.42 minus ES, which is 2.20, and the y-intercept, I think it was 1570. No, y-intercept is 3015. 3015. Okay. So I'll just press my calculator. Three times 1.42 minus 2.20 Then the answer is times 3015. Then I divide this by 2. So it's 3105 approximately. Let me repeat it again. 3 times 1.42 is that, minus 2.20 is this, times 3015, which is that. Then divide this by 2 because it is a half, which is 3105. So this is 3105. 3105, and the units, what was Z? I think Z was resistance, and since I have all these as in the SI units, so this is going to be ohms. Then determine the absolute uncertainty in E. Absolute uncertainty in E, I'll use the first part of gradient, which has E. So E is equal to 1 over the gradient plus ES over 3. I think this one is the easiest to get to the absolute. So it means using fraction uncertainties, so I have that the fraction uncertainty in E divided by E is going to be 4. This one is going to be fractional in the gradient divided by the gradient, then so I think because this is addition, there is an addition sign here. I'll first get the absolute uncertainty in 1 over the gradient alone, and I add it to the absolute uncertainty in ES over 3. So this is going to be, of course, your AS knowledge should be very important here. So first get the absolute uncertainty over the gradient, which is going to be absolute in the gradient divided by the gradient times 1 over the gradient. This one alone is the absolute uncertainty in 1 over the gradient, then plus, because this is ES over 3, so I'll just say absolute in ES divided by 3. This will give us the absolute uncertainty in E. So I'll just make a substitution. This is going to be absolute in the gradient. I think it was 128. The gradient was 1446 times 1 over the gradient, which is 1 over 1446. Then plus absolute in ES is given as 0.05. Divide this by 3. So 128 divided by 1446. Divide by again 1446. Then plus 0.05 divided by 3. So I'm getting absolute as 0.017. So the absolute uncertainty is going to be about 0.017. Now let me try to choose another method which is easy using without knowing the formula that you could use. Let me use this one here. So I'm going to use the maximum and minimum method. So I'll get E max. Because I already have E 1.42, I'm going to get the maximum value of E, which is going to be, because I'm using this formula here, so the gradient should be, if E is to be maximum, the gradient should be minimum. So this is going to be 1 over gradient minimum gradient plus ES must be maximum. So this is going to be ES maximum divided by 3. Now I'm going to make a substitution. I'm using the minimum and maximum method. So this is going to be 1 over the maximum gradient will be 1446 plus the uncertainty, which is, minus 128. That is the minimum gradient. Then plus Emax, we are going to add 2.20 plus 0.05, which is 2.25. 2.25 divided by 2.25 divided by 3. I think I forgot to change here because ES is in volts, this gradient should also be changed to times 10 to the power of minus 3. This gradient here, because 1 over the gradient, because I'm going to add here, I don't change because this and this have the same unit, so they cancel out. But this part here, 1 over the gradient. So because this is in volts, I cannot add if the units are not the same. So I have to first check that again. So 128 divided by 1446, then times 1 divided by 1446 exponent minus 3. Then I add this to 0.05 divided by 3. So that is 0.079. So this is not true. It is going to be 0.079. 0.078, not 79. 0.078 volts. So here I also have to change this because this is in volts. This one I should also change it. So I'll say times 10 to the power of minus 3. Then plus this is 2.25 divided by 3 because this is in volts. I can't add when the units are not the same. So let's check this one. So 1446 minus 128. Answer times exponent minus 3. 1 divided by the answer. Then plus 2.25 divided by 3. So that is 1.51. So the maximum value of E is 1.51. So the uncertainty in E is going to be E max minus the original value of E, which will be 1.51 minus 1.42. So 1.51 minus 1.42. So that is approximately 0.09. Okay. So either you have 0.078 or 0.09. The answers will be close to each other. So you have two methods, either the first one, if you know the formula from AS, or you use maximum and minimum values. So the maximum and minimum values is easier and direct as long as you are careful with the units. So I'll write either 0.078 volts or 0.09 volts. The experiment is repeated. Determine the resistance R that gives a value of I of 250 microamperes. So we said, remember that 1 over I was equal to, I think 1 over I was equal to 3 divided by 3E minus ES. This was times R plus, was it 2Z, divided by 3E minus ES. And this was the gradient. And this was the y-intercept. So it means 1 over I is equal to the gradient times R plus the y-intercept. So it means when I make R the subject, R is going to be 1 over I minus the y-intercept. Then I divide this by the gradient. So when I substitute, R is going to be 1 over I, so it is 1 over, because this is in ohms, I'm going to change the units. So this is going to be 1 over 250 times 10 to the power of minus 6, then minus. The y-intercept is in SI units, so I'll just carry it the way it is, 3015. Here they are not asked for the units, but it is per ampere, so minus 3015. Is it 3015? Okay, 3015, then divide this by the gradient. Of course, the gradient was not in SI units, so I'll have to change that. The gradient was 1446, so I'll multiply this by 10 to the power of minus 3 to change it into the SI units. So this is going to be 1 divided by 250 exponent minus 6. Then I subtract 3015. Then I divide this by 1446 exponent minus 3. So that is 681. So this is going to be 681 ohm. Okay, I've taken a lot of time because I have to go slow on writing on the computer. But I've tried my level best. Of course, there are teachers who like criticizing my work, yet they can't even do this, especially teachers who are struggling with teaching this. But if you're a student, you might have picked something from this. Until next time, bye bye.